So we're thinking about what are the kinds of structures in a graph and how we can discover the structure and then exploit the structure to like be able to, for example, predict what will happen in the environment or plan in the environment. And if we had some sort of simple structure that we can analyze, then that is useful, right? Like the sort of the more straightforward the structure is, the easier it will be for us to like model the structure. So for example, the one example of like something that's really simple is like if we had a lattice graph that was like this, these are like, this is sort of some world state graph, and all of the these undirected edges mean that like we have in this directed graph edges in both directions.
Yep.
So if we find this thing in the environment, that's very good. But sometimes we might not find it because like the environment just has not the structure. But the thing is that sometimes we can abstract the graph in the right way such that we get this structure. And here's a specific example. Imagine you are in a 3x3 grid world. I mean, this actually could also be a larger grid world, doesn't really matter. And you are this triangle, and you're pointing in a direction. And the actions that you can do are that you can like move forward, let's say it's W, and then you can rotate left or you can rotate right. That's all the things you can do. Okay, and now if you think about how this like graph looks, well, if you just think of this position, then we could be like, ah yes, if I'm like in this position, then I could, for example, rotate left. And then I'm like here, and then like imagine this is rotated left. I could go here, rotate it right. Or I could like rotate left 2 times or rotate right 2 times. So we have like directed arrows, like 2 arrows between each of these nodes. And that's all happening for like this particular position. So the only thing that changes here is the rotation. And the thing is now that, well, I could though also, for example, in this state here, where I'm pointing to the right, I could move forward. And then I would end up at this state. And now, well, now I could rotate left again. I could rotate left twice. I could rotate left twice, or like rotate right. Like these are, again, the rotations that I can do. And this sort of like is going here. And we get the same structure also here above. So we're always getting this thing of like we have these 4 things. So like the overall structure will look like this.
Sure.
And so like for 9 fields, we get this kind of thing.
Yep, makes sense.
So here's the human now, exactly that now we can like sort of like basically say that yes, we could just sort of like detect the structure that we have over here in this, like that these things are sort of repeating these things, and then turn this graph into another graph which basically just sort of has now these things as the nodes. So this is a node and this node is repeating. So I can say, oh, I have this.
Mm-hmm. Yeah.
And what are the edges now? It's like just, well, all of the blue edges. So we get like this in both directions, this, this, this. That's what you have. And then these edges, for example, H, would go like this. And all of the other edges we also have. They're now sort of edges to themselves. If I rotate, I don't really move from this vertex. And now, if we had this 9 by 9 grid, where we get the lattice graph, and the algorithms in a lattice graph to like efficiently represent the lattice, well, at least under certain like regularity constraints that would be satisfied in this specific case. Specifically, that's sort of like, or like a very strong case of regularity where it's easy to model it is like if always the position changes, if I move from this vertex, for example, to this, then like it means, yes, my position in the x-axis changed by 1. And that is what it means to move here. Like that's a very strong sort of kind of regularity. And then it would be easy to model this entire lattice graph, because we can just say, yes, going to the right has this effect, going down has this effect, and that's like always true. It could also be like infinitely large, the lattice. We still sort of know at any point, sort of if we know where at any point what would happen, then we can have a model for planning that is really small and efficient to run.
Yeah, yeah. Cool.